Yeah, I started 10 minutes early. Yeah, it's going to be a repeat for most of you, but not all of you. My name is Ole-Martin Mørk. I'm from Oslo, Norway, and I'm here to talk about patterns for key-value stores. I work as a scientist in Beck Consulting in Oslo, Norway, and we are looking for people. Also, we have a few Swedes, so you're more than welcome to move to Oslo. Actually, lots of Swedes in Oslo. I'm Ole-Martin at Twitter, and if you want to contact me there, I appreciate that. You can ask questions or comments or anything, and you can do it during the presentation. Today, we're going to have a short introduction, as some of you have seen, and then we're going to look at different key-value stores, look at some general key-value patterns, some Riak patterns, some Redis patterns, and in the end, look at the architecture which uses both Riak and Redis. So this is a map. It has keys and it has values. The value can be either a number or a string or a binary data, whatever you choose actually. And normally this is denormalized data. And to put data into this map, you use a function called put. It takes a key and a value. To retrieve data from this map, use a function called get. It takes one argument, the key, and it returns the value associated with this key. And to delete something from this map, you use a function called delete. It takes one parameter, the key. And when you have this functionality and you persist the data, either in memory or on disk or anything, you have a key-value store. The drawback is that these functions are hard. Using these functions is hard to search, and it's hard to follow relations, and it's hard to get really good functionality out of the data store by this small set of functions. But a lot of implementations of key-value stores supports full-time, full-text search, and it supports other more advanced functions that we're going to look into later. And if you can call this a key-value store or a key-value table if you're using a relational database. The drawback is that you get none of the advantage of a relational database. You don't get relations, like foreign keys, and you don't get schema, so you have no control of your data, but you're still putting it in a relational database. And at the same time, it's going to be rather slow with time, especially compared to the fast key-value stores. As long as the data is in the cache of the database, it's okay, but when you're starting to get disk reads and disk writes in a relational database, it gets rather slow. Because one of the main causes for using a key-value store is speed. Most of those data stores are really, really fast. And another cause is the distribution. Most of the key-value stores support some kind of distribution of the data, and by using that, you get better fault tolerance and better performance. But the most important cause in my mind is that our data often fits better in a key-value store compared to a relational database. People have been bashing the ORM tools for a long time, and I will not continue doing that here, but just let's say they have a good point. A lot of the data we deal with on a daily basis fits better in a key-value store than a relational database. For instance, say you want to store a person. It has several addresses, several email addresses, Facebook, phone numbers, Twitter accounts. And if you want to store this data in a relational database, this is your database structure. It's the only way to achieve one-to-many relationships in a relational database. But this isn't your data. The data is the person that has some attributes. And the only way you have to model it like this is because of the restrictions the database puts on you. And you want like a normalized database and such. In a key-value store, this would be solved in a much better way, like this. This shows an example from MongoDB with denormalized data and schemaless design. And it's the data and how you use the data that decide how the data is stored, not the other way around. And there's a lot of different key-value stores out there. The simplest databases only allow get, set, delete, but lots of other of these up here has possibilities of full-time search, full-text search, grouping of data, map-reduce algorithms. And a really simple database that just support get, set, delete is HTML5 local storage. Okay, so now it's new for everyone. So this is some JavaScript. And in order to write data into local storage, it says local storage.key equals value. And in order to retrieve data, you'd say local storage.key. And if you do like that, it's stored in the local storage. And I don't have an example of delete, but you can figure out how it looks. And it's easy, but it works. Another database, really central database in the key-value landscape is MongoDB. And there was a talk about MongoDB this morning, an hour ago, so I guess some of you were there. It's a document database, but since it stores values associated with keys, it's also a key-value store. And what's special about the document database is that you store documents, of course, but most of the document databases can access the data based on other keys than just the primary key. You can search for other properties of the data. And you can easily update parts of the document. A standard key-value store has just a put, but MongoDB you can update like street address on a person. And this gives a whole other pattern of usage than simple key-value stores. A third type of key-value store is Cassandra. There was a talk about it yesterday also. In addition to pure key-value usage, it has the concepts of columns, supercolumns, column families, and super-column families. And it can scale out of this world. It's the largest cluster I've read about had 400 nodes running in production for one database. So if you have lots of data or extreme load, you might look into Cassandra. In addition to this, you have grids and lots of databases. And the reason I'm mentioning all these data stores is to show you that a key value store doesn't mean one thing. You can't say anything more about the database than it's possible to retrieve data based on a key. And that's not much. And these databases have really different properties. Some are good at scaling, some are good at speed, some are flexible on consistency, some have a lot of functionality related to organizing your data, and some are good at search, etc. And when it comes to patterns for key value stores, it gets hard because they are so different. There are a few general key value store patterns that I'm going to show you, but then I'm going to focus on Redis and Riak patterns. The reason I've chosen Redis and Riak is that they are really powerful, yet really different data stores. And they're rather pure key value store. You don't store documents there, and you don't relate to super column families, etc. And they work really good together, and it fits really good into the one architecture, which I'm going to show you at the end. But first, the general patterns. Keys are, of course, central in a key value store. And good naming of these keys are important. What you see here is a good starting point for a key name. You can call it an URI or name spacing. So first we have the name of the application. Then we have the space within that application, domain or whatever you call it. Then you have what are you storing, then an ID. So say you have a CRM solution, so it's like CRM, colon customers, colon person, colon the ID of that person. In that way, you can look at the key and you know what it is, and it's easy to don't conflict with other keys. You can have control of the ID number of each person, but since everything is organized in the same space, you need some kind of naming conventions in order to not get conflicts. And if you have a good key structure, you can achieve a lot. Retrieving data based on primary key, or it's just one key, so key, is generally hard. To retrieve data based on other than the key, it's generally hard in a key value store. Let's say you want to retrieve these data based on the Twitter handle. You don't know the user ID 1234. You just know my Twitter handle. Initially, that's impossible, but it's a little trick. You can create a new value, which points back to this one. So you retrieve user Twitter Ole-Martin, get the ID of that data, and retrieve that. You get two lookups, but you get the functionality. The same thing you can use in order to control relations between data. Through good key design, you can see here that this is a user. You can easily get a relation, and you know what you're pointing to. This way of solving this challenge has some problems compared to relational databases. Like, you don't get any of the foreign keys benefits. You don't get any cascading deletes, etc., and you don't know if the data behind user ID 1234 actually exists. But you get, and you have to run 2 queries to get 2 lookups in order to get the data. But it works. And it's hard to have a data system that doesn't have relations between data. And this is one way of solving it for a key value store. Let's talk about hashing. Hashing is important in a key value store. When you have distributed data, you have to know where the data is stored, at what server. And in order to get, if you have, let's say you have 4 servers, and in order to get to know which server a given data is stored, you have to do something. And the easiest algorithm for this is what you see here. You take the hash value of the key and modulo the number of servers. So if you have 4 servers and for simplicity, the hash you're sending in is 7, 7 modulo 4 is 3, and you have the server ID. So you access server number 3 in order to retrieve the data you were asking for. And if you have a data set laid out linearly like this, if you have the need to add another database server in order to gain better performance, or the disks are getting full or something like that, the data is going to be moved all over the cluster. Data is copied from server 1 to 2, 2 to 3, 3 to 4. It's a lot of network traffic just to add one server, and you have to rebalance the cluster right away in order to put more servers into the cluster. It's a better way to do this, and it's called consistent hashing. Here you distribute the servers on a circle where you have, let's say you have a value 0 here, and just a little bit to the left you have integer max value. And when you get a hash, you hit one spot on the circle. And then you search backwards on the circle in order to hit the server that has the data. This can also be used for storing the data on several servers to distribute your data. For instance, let's say that you want to store your data on minimum 2 servers at a time. And here we hit the circle, and we're going towards server A to retrieve the data, but that's disappeared. Then we find the data at server C instead. Another big advantage of consistent hashing is that it's really small amounts of data that has to be moved in order to add another server to the cluster. If you compare to the last line where all servers were affected when we added one new server, if you add a server D here, it's just server C that is affected initially. Over time, the data will be balanced, either by you rebalancing during the night, or you just take your time and it will balance out. But you don't have to do the balancing right away like you had to do with the previous solution. So, when is it smart to use a key value store? The simplest thing to do in the start is to combine the relational database and the key value store at the same time. You can use it as a cache, like many people use EH cache or memcached today. You can use it as a calculation machine that you store the data in the relational database, but all calculations, sorting, grouping of data is done in the key value store. It's the same as the cache, but it's much more advanced cache, and it's much faster than a relational database. But if you want to get rid of the relational database altogether, you have to find a use case where it fits. And for instance, web pages fits well. All web page has a unique reference, like a URL. It fits. Preferably a document database would work really good for that case. Another good candidate is a product database. All units have an ID. You have really few relations between the data. And it's really critical that you don't lose any of the data. I will get more back to this example later on. Now we're going to talk about Riak. Anyone worked with Riak here? Good, 2, 3. It's a really nice database. You can access it through REST, JavaScript, or Erlang. I guess most Swedes know Erlang. Because if you want to use it in the best way, you use Erlang, but you come a long way with JavaScript as well. The central feature of Riak are buckets and keys. You stored all keys in the buckets. And buckets are like domains or namespaces or whatever you call it. But the most important thing about Riak is how it relates to the CAP theorem. And the CAP theorem says a whole lot about the database. It says that, like Jonas Bomer mentioned just before now, it says that it just can have 2 out of these 3 properties on the database. So if you want consistency and partition, you can't have availability at the same time. So then you will need to have the data available. So that's not a good choice. Anyway. But the problem is that it's not like if you drop consistency, it's not like your data is 100% inconsistent. It's just that it's not 100% consistent. And what's proven is that these rules doesn't necessarily count for one database. It's count for one moment in time. And Riak has taken advantage of this and let you, for every request, tune between consistency, availability, and partitioning. Actually, between consistency and availability. And they do it by these 3 parameters. N says how many nodes you're going to read from or write to. W says how many nodes that should have successfully written before you consider it a success. And R says how many nodes you should have successfully read from in order to consider it a success. By an example, if you have you write data and you say you're going to write it to 5 nodes, but you consider it a success if 2 of them returns successfully. Then it's going to be fast, you're going to have high availability, but you don't know what happened to the other 3 servers, so the consistency might be rather bad. But if you say that you want 5 successful writes, it's going to be slow, but at least you have consistency. And the same goes for reads. You say that you're going to read from 5 nodes, but you're happy as long as 1 of them returns. You get really high speed, but you don't know if you retrieve the latest data. You don't know anything about the consistency of the data. And this flexibility you can control per bucket, per read, and per write. And that gives a unique flexibility, because it's not like all the data in your data system has the same need for consistency. Something is critical that it's always consistent, like money transfers, but like a register of people might have a smaller amount of consistency necessary. So let's look at some Riak patterns. MapReduce is a central feature in Riak. If you're going to search or run calculations on your data, you have to use MapReduce. The good news is that you don't have to write it in Erlang. You can write it in JavaScript as well. And MapReduce in Riak looks at some input data. You can either use a key pattern or a bucket. And the algorithm will then look at all these data, and if you given the keys a good name like this, you can either look at all shopping keys, or all keys for a given date, or all keys for a given user ID, and run the algorithm on that. But what's important to remember when it comes to MapReduce in Riak is that this algorithm is mostly meant to use for batch operations. If you use it for real time, it's going to, as long as the cluster grows, it's going to be too slow to use. You can also use something called secondary indexes in Riak. Using secondary indexes, you can do quick lookups on metadata at your keys. If you have any group information, you can put this in the secondary index, and you will have your data much more easily available. You can use this index to keep an eye on your relations between data, and suddenly you have relations in the key value store. If you look at this example from earlier, we had to use 2 lookups in order to get the data. By using secondary indexes in Riak, you have one place where you add the metadata, and you can retrieve these data based on all these keys. The drawback of using secondary indexes is that, as you remember from the consistent hashing circle, by using the key, you know which server the data is stored on. But by using secondary indexes, the system doesn't know which server the data is stored on. So it has to send a broadcast out to the whole cluster, and hopefully someone will answer, yeah, I have the data, and you retrieve the data. But the load on the complete system grows. Riak has also functionality to run code before or after a commit. Pre-commit can be used for validating the data, validating that the secondary index match the values that actually stored behind the key, because Riak doesn't have that validation by default. And you can implement pre-commit in Erlang or in JavaScript. Post-commit, you have to write in Erlang, but you get some nice feature with it. You can send an SMS to the user when his profile is updated. You can update a cache, or you can update an RSS feed so other databases can listen to the data in Riak. You can get many steps towards a polyglot persistence architecture by using these post-commits. So that's Riak. Let's look at Redis. Redis is a really fast in-memory key value store. In memory, so it's fast. And it has also a lot of interesting data structure. The database stores all the database in memory. I said it 3 times now, I think. The limit there is that you can't have more data in the database than you have available memory. The data ends up at the disk at some time, so you can take backups, etc. But it has to be in the memory all the time. All operations are atomic, and the database has support for some kind of transaction management, but it works. Redis has these normal get, set, delete operations. In addition to that, it has strings, which is atomic increment operations, appends, substring, etc. It has a hash, store a map on a key. And this can be easily transferred to Java objects. You have lists, like arrays and linked lists and such. You have a set, the same as set in Java, but you can also do really good intersections and unions and stuff. And you have sorted set, which is the most powerful data structure in Redis. All values in a sorted set has a value and a score. And by combining these two, you can create some really powerful features. So, some Redis patterns. This is a query that almost all the time takes too much time to run in a relational database. In Redis, sublists like this limit thing and sorting is part of the core functionality, and it's really fast. And then the nice thing about the documentation for Redis is that all operations has O notation. So you know how long it's going to last. It's not dependent. If it's dependent on the size of the set, it says so in the O notation. And since Redis is so fast, it can be used as a cache, of course. And the difference compared to a regular cache is that this can be much smarter. You can store all foo elements at the relational database, but then do the sorting and the sublisting in Redis. And the good thing is that means that it's not that important that Redis isn't consistent, that it's eventually consistent, because the master data is stored in the relational database. And since Redis has atomic operations for counting, it's really good at that. And it's good at keeping an eye on statistics. For instance, if you want to show a user a banner when it's read 10 articles on your web page, it's really easy. And if you have 1 million users and you want to just show one user when the count reaches 1 million, since it's atomic, you know it's going to work. You don't have to worry about it. Like, if you want to know how many pages a user has read, you use the atomic increment operations. If you want to use to see which article which is most read today, you use the sorted set range by score operation. And you want to know how many unique visitors you have, you use a set which only holds unique values, and you use the scard operation, which is a count operation. Just one side note about Redis, since it's so fast and it's possible to write Java objects as values, you need to use a quick serialization operation, quick serializer. I've used Clio and find it really useful, but as you can see, don't use regular Java serialization. It's slow. And the last thing we're going to look at is the combination of Redis and Riak, because that is true love. As I said, Riak is really good at storing critical data because you can tune the consistency. So you can combine both critical data and not so critical data. And you can distribute the data on several servers and keep your data safe. And in Riak, you can have bucket products where we add key value pairs with products. After each commit to Riak, we send an update to Redis with the data which is now updated. Plus, we write the data to an RSS feed, so we have a history of data added to the system, and we can put these data into Neo4j or any other database if we want to use that later on. We have the history, so we can recreate the data in any database we want. In Redis, we store the same map as we stored in Riak, like a catalog with product ID, catalog.product_ID with binary data. And then we can also store some helper sets, like how many products is sold today, and which products is most, and we can sort it on number of sold per product, and week and year, and only mind takes the limit on that's what you can do with Redis here. So by combining these two databases, you have a ring of Riak servers, which is really stable. You keep your data safe and consistent. And we have a Redis server, which make sure the performance and the speed of the system is really fast. The drawback is that you spread your data in several systems, and you get duplication of data between several systems, and you have to know different technologies, not just one database. I guess that's why you're at the conference, to learn new technologies. And new technologies are fun. So that shouldn't be any problem. And as long as you know where the master data is, it's in the Riak cluster. That's the most important thing. So all your writes are sent to Riak, then you can have as many copies as you like. So, to summarize. There are a huge amount of different key value stores available, and it can be hard to choose, but those two I've mentioned here are really good and easy to start with, and you can look at MongoDB and go full-flexed Cassandra if that's your cup of tea. Use good key names. It's really, really important. That's the main thing you have to remember today. And make sure you model your data correctly, even though it's because it's schemaless. It's you get a lot of freedom, and you can end up with a really chaotic database because it doesn't. You don't have a DBA which says how you're going to model your data. So, but do it. Model your data correctly. Make sure you use a database which provides consistent hashing. Use if you haven't used any key value stores at your company or at your customer so far, don't go to your DBA and say that we're going to stop using relational database. Now it's all key value stores. Use both at the same time, and then you can kick out the relational database. But only if you have data and usage that matches your key value store architecture. If like reporting is the most important your company doing, then stick to the relational database. And yeah, that goes with that. Use the data store where it excels. Like don't use it just to use it, and use it where it's really good. Combine different key value stores and different databases altogether. Like Neo4j is really good to combine with a key value store if you have the time. Rikard Öberg, which is, I don't know if he's speaking here today, but he has a really good video at nosql tapes talking about using key value stores, Neo4j, search engines together in one architecture. And be creative. It's fun. So, any questions? Jag förstår svenska. Ja. So the question is if I know of any good websites that do a comparison of data NoSQL stores. And no, I don't. There's this page called NoSQL tapes, which interviews a lot of advanced NoSQL users, and they tell about how they use their data stores. That can be good. And there are some good articles on Wikipedia, for instance, that at least has some links you can follow, and you can understand the difference between document database, pure key value stores, column-oriented, and relational databases. Yeah. Yeah. What's the difference between Dynamo and Riak? Yeah. Dynamo is a column-oriented database, as I think, yeah. And so that has it's more like Cassandra. It has columns and super columns. So you have some kind of schema between your data. While Riak is more of a pure key value store, which has just keys and buckets. While, as I think, at least, that Dynamo has several columns that you store your data in. I haven't used Dynamo yet. Okej, tack så mycket.